Hi, I'm Lingxiao from Microsoft Research. Today, I will introduce our work later, enabling efficient low-precision deep learning computing through hardware tensor transformation. Recently, scaling DNA models to larger sizes like large language models pushes the computation from single precision to lower bit like half, FP8 in 4 to improve the computation efficiency and save memory. I also searched the 4-bit models on Hugging Face and issues more than 200 new 4-bit models in 1 week. On the other hand, hardware vendors also introduce low-bit computation to improve the computation power. For example, NVIDIA achieves 1,000 times of T-flops improvement by pushing single precision to FP4 in the past 10 years, while the single precision T-flops improves only less than 1 magnitude. Both model and hardware have the trend of larger size with fewer bits. However, supporting low-precision DNA computing is challenging. On the model side, new data types are fast evolving in 3 directions. First, the numeric precision is becoming lower from 32-bit to 16-bit and even 1-bit. Second, the group-wise precision scaling is required in some data types like MXFP for better model accuracy. Last but not least, mixed precision operations are becoming more and more popular due to the different sensitivity of activations and weights in DNA models. For example, the widely used GPT-Q uses int4 in model weight, while uses RP16 in activations. On the hardware side, it's insufficient to support these fast-evolving data types. When there is no support for a new data type, user needs to use proxy data types to represent the computation. For example, representing the new RP4 data type with RP16. Moreover, the supported low-precision computing is still inefficient. According to our evaluation on matrix multiplication of the supported RP16 and int8 data types on NVIDIA and AMD GPU, the average utilization is less than 60%. Here is an example to describe the inefficient and insufficient support for low-precision computing. A matrix multiplication of a RP16 matrix and a RP8 matrix. Assume the hardware has 4 hierarchical layers of L2, L1, L0 memory and the core, which is similar to the global memory, shared memory, register, and the tensor core in NVIDIA GPU. We assume L2 and L1 require a 8-byte transaction, which can be saturated by 4 RP16 value or 8 RP8 value. The L0 requires the low matrix injection of a M2, N2 shape of RP16 value, and the core requires the MMA injection of multiplying 2, M2, N2 shape of RP16 value. When loading the RP16 matrix A and the RP8 matrix B from L2 to L1 is good because it satisfies the 8-byte transaction. However, when loading L1 to L0 with a low matrix injection, the required data layout does not align with the memory transaction of L1, resulting in only 50% utilization. Furthermore, the RP8 matrix B cannot be loaded from L2 to L1 with the RP16 low matrix injection due to data type mismatch. Even though matrix A and matrix B are already in L0, the core even cannot process the multiplication of RP16 matrix and RP8 matrix due to the data type mismatch. This example shows the reason of current inefficient and insufficient support for low precision computing. The reason is because the computation-coupled scheduling usually results in mismatches in hardware hierarchy. To enable efficient low-precision computing support, our first insight is to decouple the computation and storage during scheduling to allow data flexibility in each hardware layer. For example, when load matrix A from L2 to L1, the data layout can be transformed to align the requirement of the load matrix injection, which can enable full utilization of the L1. To process the unsupported FP8 type, we observed that low bit data type can be converted to a lossless higher bit data type. So when load matrix B from L2 to L1, the data type can be converted to FP16 in L1, which is supported. Then the loading of matrix B from L1 to L0 can be successfully conducted with the load matrix injection. As both matrix A and B are FP16 in L0, the MMA computation can be conducted by the core. Therefore, we can leverage transformations to align the required computation with hardware support. Based on these insights, we designed a ladder for efficient, low-precision deep learning computing. However, the first challenge is imposing the representation for evolving data types. Our solution is a type-tile or T-tile abstraction. Specifically, the evolving data types are represented as T-type, which is a group of homogeneous n-bit elements. Then, a T-tile is the tile-based tensor abstraction augmented with T-type. Then, the data type information in the tensor-based model representation can be explicitly exposed. Furthermore, the hardware support can also be represented as T-tiles. For example, the low matrix injection requirement can be represented as a T-tile of 2-dimension shape of IP16 value, or of IP16 type. Yeah. The type-tile abstraction implicitly exposes the data type information of both model and hardware. However, T-tiles from model usually mismatch the hardware requirements. And our solution is decoupling computation as a pipeline of T-tile transformations that transform loads, loads a T-tile from lower layer and transform it. The computer processes a T-tile computation on the core. The transform store transforms the T-tile and store it back to lower layer. And we introduce 4 T-tile transformation primitives: slice, map, pad, and convert. Slice can slice a T-tile from the input T-tile, and map can modify the T-tile data layout. Pad can pad the T-tile's shape, and convert can convert the T-type of the T-tile to another T-type. Let's return to the example. The load of matrix A from L2 to L1 can be represented as a transform load with slice and map, while map modifies the data layout. And the load of matrix B from L2 to L1 can be represented as a transform load with slice, convert, and map, while the converter primitive converts the data type from IP16 to from FP8 to IP16. Then loading matrix A and B from L1 to L0 can be successfully conducted by with full memory utilization by the IP16 load matrix injection. Finally, the T-tile computation can be successfully conducted on the core with the IP16 MMA instruction. However, the T-tail transformation introduces much larger space over the existing tile-based end-to-end model scheduling. It may also introduce a new latency memory trade-off that it can trade off memory consumption in lower layer to reduce the transformation cost in higher layer. And our practice is to consider tiling and transformation separately, which is effective according to our evaluation, but it's potentially suboptimal. In brief, it includes 3 stages. In the first stage, the transformation provides hardware hints about the preferred data set granularity. Then the tiling schedule leverages the hint to decide the tiling. Then transformations are scheduled on the given tiling. And the detailed policy can refer to our paper. Ladder's implementation is open source. It supports PyTorch and OSENIX as model input and represents the input model as a T-tail-based data flow graph. Then Ladder schedules the input T-tail-based graph to a schedule plan. The scheduling is implemented on top of welder and roller with new transformation mechanism and policy. Then the schedule plan is generated as device code for execution. The cogent part is on top of TVM with new PTX and ISA level optimizations. We also implemented the heap backend in TVM for AMD GPU. Furthermore, the key component of Ladder has also implemented as BitBlast, a PyTorch operator library to empower low-precision computing in existing deep learning ecosystem. We have implemented the integration with frameworks like PyTorch, VLM, AutoGPTQ, BitNight, BitDistiller for low-precision model deployment. We evaluated LLM inference with real-world low-precision data types on NVIDIA A100 GPU. Ladder achieves 10% speedup over the state-of-the-art compiler Welder and the state-of-the-art inference library from NVIDIA, TensorRT. When comparing on the widely used W-int4A IP16 in GPTQ, Ladder achieves 2 times speedup on average over VLM. When comparing on the latest W-int1A-int8 in BitNight, only Ladder can support this case with 8 times speedup over IP16. We also evaluated Ladder on different data types for the Llama 2 model. Ladder shows efficient support over data types of different bits from 16-bit to 1-bit. Rather than LLMs, Ladder also supports many other DNA models like vision and speech models. Ladder shows speedups compared to Welder and TensorRT and achieves up to 3 times speedup when enabling low-precision computing. On the compilation time evaluation, Ladder can compile an end-to-end model in less than 1 hour, which achieves magnitudes of compilation time speedup over TensorIR and AMOS. Low-precision models can achieve real speedup with Ladder, so we evaluated the efficiency and the accuracy of different low-precision methods from 16-bit to 1-bit on different sizes of the Llama 2 models. The evaluation shows 4-bit weight quantization achieves similar accuracy compared to the IP16 model, while the 7-bit low-precision model can outperform the 3-bit IP16 model on both accuracy and efficiency. Finally, it's noticeable that the BitNight 3-bit model outperforms the 3-bit IP16 model on both accuracy and efficiency. These results show good potential of low-precision models. We also evaluated Ladder on AMD GPU. LiDAR achieves about 3 times speed up on average over welder on MP16, while achieved another up to 3 times speed up when enabling low precision computing. Let's conclude. The increasing low precision computing is observed in deep learning, and the LiDAR proposes type-to-tile abstraction and hardware-aware tensor transformations to provide a systematic solution for low precision computing. We hope LiDAR and our open source BitBlast library can empower both model designers and hardware vendors in taking advantage of the trend of low precision computing. That's all. Thank you.